Spin a gyroscope and it does something physics says shouldn't happen. It floats, tilts, and defies the pull of the Earth. The moment you hold a spinning gyroscope, you feel it. There's a resistance, a pushback. You try to tip it over and instead it wobbles sideways in a way that seems to mock gravity itself. But it's not magic. It's not defying anything. What you're witnessing is one of the most elegant demonstrations of motion in the physical universe. And the strange part, it's been hiding in plain sight. Here's the question that stops most people. Why doesn't a spinning gyroscope just fall when you tilt it? The answer isn't that it's stronger than gravity. It's that motion itself has a kind of stubbornness. In physics, we call this inertia. But rotational inertia, the resistance of a spinning object to change its axis of rotation, is something else entirely. It's the invisible force that makes the gyroscope behave like it's alive. Let's start with the basics. A gyroscope is just a wheel, a heavy wheel spinning very fast around an axis. That's it. But when it spins, something remarkable happens. All the mass in that wheel wants to keep moving in the same direction. Every particle, every atom resists any change to its path. This resistance is rotational inertia. It's the reason a spinning top stays upright. It's why a bicycle wheel, once spinning, doesn't want to change direction. But here's where it gets interesting. What happens when you apply a force to a spinning gyroscope? You'd expect it to tip over, right? Gravity pulls down, the gyroscope falls. Simple, except it doesn't. Instead, something called precession takes over. The gyroscope moves sideways. It wobbles in a circle instead of falling straight down. Why? Because the force you apply, gravity, doesn't act on the gyroscope the way it acts on a stationary object. This is the core of the mystery. When gravity tries to change the axis of rotation of a spinning gyroscope, the gyroscope's angular momentum, the spinning motion itself, pushes back. But it doesn't push back in the direction you'd expect. It pushes perpendicular to both the force and the spin. This perpendicular response is precession. It's not defying gravity, it's obeying a different rule. Think of it this way. Imagine a spinning bicycle wheel. You hold it by the axle and try to twist it to one side. The wheel doesn't resist the twist by staying still. Instead, it resists by rotating in a direction you didn't expect, upward or downward. That unexpected direction is precession. It's the wheel's way of conserving its angular momentum while responding to your force. The faster it spins, the more dramatic the precession. The slower it spins, the faster it falls. Now let's talk about angular momentum. This is a quantity in physics that describes how much rotational motion an object has. It's calculated by multiplying the object's moment of inertia, basically, how its mass is distributed around the axis, by its rotational speed. A gyroscope with high angular momentum is stubborn. It resists changes to its spin axis with tremendous force. This stubbornness is what makes the precession so pronounced. Here's a question worth asking. If the gyroscope is precessing, isn't it still falling? Technically yes, but not downward. The axis of the gyroscope traces a slow circle in space. This circular motion is the precession. The gyroscope is falling but sideways. It's a beautiful compromise between gravity and angular momentum. One pulls down, the other spins stubbornly. The result is this graceful wobble. The mathematics of this is elegant. The rate of precession depends on the torque applied, in this case, the torque from gravity divided by the angular momentum. Faster spin means slower precession. More torque means faster precession. It's a perfect inverse relationship. Change one variable and the gyroscope's behavior changes in a predictable, almost musical way. But why does this matter beyond the toy spinning on a string? Because gyroscopes aren't just novelties. They're in your phone, keeping track of orientation. They're in aircraft, stabilizing navigation. They're in spacecraft, controlling orientation in the weightlessness of space. Understanding precession and rotational inertia is understanding how we navigate the world. There's another layer to this. A gyroscope in free fall, in space, or even in an airplane during a dive stops precessing entirely. Without gravity applying a torque, there's no force trying to change the spin axis. The gyroscope simply spins. It maintains its orientation perfectly. This is why gyroscopes are so valuable in spacecraft. They don't need gravity to work. They work because of the object's own rotational inertia. Now we arrive at the real answer to our original question. A gyroscope doesn't defy gravity. It obeys it perfectly. What it does is respond to gravity in a way that feels counterintuitive because we're not used to thinking about rotating objects. Gravity tries to tip the gyroscope over. The gyroscope's angular momentum resists. The two forces interact, and the result is precession, a sideways wobble instead of a downward fall. The invisible force isn't actually invisible. It's motion itself. It's the stubborn refusal of a spinning object to change its path without a fight. It's angular momentum, precession, and rotational inertia working in concert. Once you see it, you can't unsee it. Every spinning thing in the universe is following these same rules, from gyroscopes to planets to galaxies themselves. Subscribe, there's a new invisible force waiting to be discovered every week. Subscribe, there's a new invisible force waiting to be discovered every week.